My name is Yaga Richter. I'm a scientist at NCAR and a lead organizer of the NCAR Explorer series. It is my sincere pleasure to welcome you today to the MESA Laboratory and the third lecture in the NCAR Explorer series. NCAR, or the National Center for Atmospheric Research, is a world-leading organization dedicated to the study of the atmosphere, the Earth system, and the Sun. Our scientists and engineers are very passionate about the work they do here, and through this series, they share their passion for scientific discovery with you and the global audience through our live stream and archive presentations on UCAR Connect. Thank you for taking the time today to join us. Today's speaker, Scott McIntosh, has a great passion for studying the sun, stars, planets, and galaxies, and you are in for a real treat. Dr. McIntosh was born in Uddingston, Scotland, a village of 10,000 people between Glasgow and Edinburgh, and attended University of Glasgow. As an undergraduate, he studied mathematics and physics and pursued internships in medical physics and medical imaging. Scott fell into astrophysics and solar physics by accident. He was convinced that the medical imaging skills he had learned could be applied to understanding the complex hot plasmas of the outer atmosphere of the sun and the stars. He then started his PhD in solar astrophysics at the University of Glasgow under the guidance of Astronomer Royal of Scotland. Dr. McIntosh was a postdoctoral fellow in NCAR's Advanced Study Program from 1999 to 2001. In 2001, Dr. McIntosh left NCAR to work with the European Space Agency at NASA Goddard Space Flight Center to be an instrument scientist for the Solar and Heliospheric Observatory, or the SOHO mission. From 2004 to 2007, he worked in Boulder at the Southwest Research Institute on a number of solar projects and missions. In 2007, Dr. McIntosh returned to NCAR and worked as a scientist in the High Altitude Observatory, or HAO. He quickly advanced to being the section head of HAO's Space, Weather, and Solar Transit Research Group, and since 2014 holds the position of the Director of High Altitude Observatory and Associate Director of NCAR. Dr. McIntosh is also an avid soccer player, coach, and fan. He and his 4 kids have set up their basement as a mini training facility so they can practice year-round. Scott has been known to coach more than one soccer team each season, so look for him at the St. Vrain's Football Club's games in the fall and spring. Please join me in welcoming Dr. Scott McIntosh.
Good afternoon, everyone. Hope you're all sitting comfortably. Take your glasses off, because you won't be able to see anything. Did I get the school teacher in to deal with you? No, I'm kidding. Good afternoon, everyone. So in the next 45 to 50 minutes, I'm going to give you a parade through some parts of our solar system, specifically the sun, the moon, and its interaction with us. And I hope to end with providing you some details about a small event that's going to happen about 350 days from now, just a little bit north of here, called a total solar eclipse. You notice here, beautiful image on the left is actually the first ever recorded picture of an eclipse, and it was taken in Königsberg, Prussia, in 1851. And it provides a kind of perfect slide. Like every bad talk, we must start with an overview. And so since this is going to be a bad talk, you must have an overview. So we're going to start with an overview of the sun itself. What is an eclipse? How did ancients think about eclipses? What are you seeing when you see an eclipse? Can we understand a little bit about the solar atmosphere? In doing that, we're going to take a small tour of the layers of the onion, the layers of our star, the sun, and then get to points where we start to think about how we're going to study certain pieces of its atmosphere. Before we dive into the reality of why do we study the sun in our technological society. A little bit about my home base, NCAR's Solar Terrestrial Physics Lab, or HAO, the High Altitude Observatory, before we dive in to the last 10 or 15 minutes or so on the 21st of August 2017 total solar eclipse, or as it was dubbed by one of my colleagues, the Great American Eclipse. Then, of course, to wrap up, I get to pose a challenge to the audience. You get to sit a test. If you fail the test, you don't get to leave the room. It's just my privilege. Okay. So as you may or may not know, we live in the atmosphere of our star. Our tiny little planet is bathed constantly with light and energetic particles that come from the sun. Now, we're kind of lucky. As much as we need that light to live and to grow food and to do just about anything, the energetic particles are profoundly destructive. They're profoundly destructive to any piece of electrical infrastructure, power grids, your laptops, your cell phones, anything that you would plug in is vulnerable because they're all connected to a power grid. Now, you will notice when this thing loops through that our little blue dot is protected. As these particles come streaming in from the sun 93 million miles away, you see they get deflected. It's kind of like, well, I guess it's not like bugs on your windshield, but they get deflected around our little planet. Can you see it there? Why is that? The clue comes in the next phase of the movie when the Earth gets hairy. The hairs coming out of the Earth are its magnetic field. And that magnetic field uniquely acts to save us from those particles from the sun. And if you don't believe me, I guess you should probably find a Martian to ask about the relevance of magnetic fields on their atmosphere.
Eclipse. The moon moves between the Earth and...
Do you want that? It's better than me. Okay, so what is a total solar eclipse? A total solar eclipse happens when the light... I'm going to jump this back, excuse me. A total solar eclipse happens when the moon blocks out the light from the sun. And by happenstance, the moon is 400 times smaller in diameter than the sun. But luckily, it's also 400 times closer to the Earth than the sun. So, at certain points in its orbit, it completely blocks out the light from the disk of the sun and leaves us with an astonishing image of something that you can't normally see unless you've got millions of dollars of really cool research hardware. Now, why does it do what it does? So it depends on 3 different cycles. What sets the eclipse? An eclipse has 3 components to it. If you want to predict it, you need to understand where the sun is relative to the Earth. That is a period of 364.25 days. You also need to understand where the moon is relative to the Earth and relative to the sun. And that has an orbit of about, or a period of about 27, give or take a day or half a day. And then you also have to understand where the moon is relative to the angle between the two. And it's in an elliptical form, and it wobbles north and south. And every now and again, those 3 things come into combination. And when those 3 things come into combination, you get a shadow on the Earth because now the moon and the sun are one, or they appear to be one in the sky. That shadow traces its way across the planet, and blocks out the light for several minutes for those that are sitting in the shadow. Now, if you're not directly in the shadow, you may be in what we call a partial eclipse. And in a partial eclipse, the sky won't go dark, the birds won't start chirping, the birds won't stop chirping, and several other things that you won't get. So if you can, get to totality. So there's several phases of a solar eclipse. There's a partial eclipse, when the moon first tries to take a bite out of the sun. Then eventually, as the moon transitions across from west to east, it starts to create a gradually more profound bite of the sun where Pac-Man is no longer there and you're left with a very faint crescent of light before the moon is completely eclipses the sun and you're left with a very faint halo around the sun. Does anybody know what that halo is called? The corona. Well, we'll get some good people in here. We'll talk about the corona in the next slide. And before 1942 or thereabouts, the only way you could see the corona was from total solar eclipses. I'd like to say that now we have far more advanced technology that allows us to see it every day and study it in great detail. But of course, as the moon continues to pass across the face of the sun, we now start to see the reverse. And this is the part in a total solar eclipse when everybody just starts talking and going, woo, that's awesome. They forget about the poor 3rd and 4th contact. They shouldn't be neglected. They're important parts of an eclipse too. So I mentioned the corona. Then we want to guess what drives the corona because I'm recording this. The corona is a very, very mysterious gas that exudes from the surface of the sun. And it's really a puzzle. In fact, it's one of the key cornerstones for our interaction with our star, and it really still puzzles us to this day, even though we've been observing it daily for almost 75 years. Now, we'll get to that in a minute. But what does a total solar eclipse look like from space? So here's a weather satellite that sits in a geosynchronous orbit around our planet. You see that big shadow? That's not the Death Star. That is actually the shadow of the moon blocking out the light from the sun directly. And because you're on a geosynchronous satellite, of course, it's just sitting over one location, so it sees this shadow coming behind it. It's really beautiful, but imagine pretty eerie. Now, we also have a very cool piece of hardware out at the gravitational balance point between the Earth and the sun. It's about 1.5 million miles from here. There's an observatory called Discover. And that observatory called Discover has a telescope that looks back at the Earth. Now, that telescope looks back at the Earth every now and again, gets to be blocked out by the moon. And so this isn't Photoshop, this is real. It looks like Photoshop, but it's not. So back in the day, the ancients were kind of mysterious people, right? But the sun was even more mysterious to them. The moon was a mysterious body to them. And in fact, over millennia, they collected information about the stars and the planets and the moon and the sun, and started to even build things like Stonehenge up in the top left, which was actually a calendar. And that calendar actually could predict eclipses. Now, back in I believe it was the 23rd century BC, the first recorded eclipse took place. And it's up in the top right-hand side of the slide, out in Mesopotamia. And they believed that the sun had been bad and it had been banished for several minutes before it appeared again in all its glory. There are also beliefs that Akhenaten changed the religion of Egypt based on a total solar eclipse. There are many things. Christopher Columbus actually used a lunar eclipse. It was quite subtly different from a total solar eclipse to bamboozle the natives because he knew when it was going to happen and where. And it was a way of him exuding his power over the natives because they were in awe. And in fact, there's many instances where native populations have been in awe because people with very great power and pretty good math skills were able to predict exactly where and when an eclipse would occur. Can you imagine someone saying, I'm going to make the sun disappear. I'm going to make the midday sky black. Hold the hand up, it goes black. That would be pretty cool. It would be pretty cool if it would also mean that people lost their lives. And down in the bottom right-hand corner here is some ancient Chinese philosopher, actually an astrologist, not to be confused with an astronomer or an astrophysicist, or my former boss, the Astrologer Royal for Scotland. And that they incorrectly predicted eclipses, and they were a few decimal places off and lost their heads as a result of it. In fact, there's kings, like this poor guy here, King Henry I on the far left-hand side here, who died on the day of an eclipse. And it became known then that it was a bit of a bad omen for royalty. That, the eclipses were a bad omen because they would typically die on that day, given one instance. Now, as I indicated, about 22, 23 centuries ago, maybe even a little bit earlier, out in the Middle East, in Babylon, they'd observed eclipses and stellar phenomena for centuries, keeping incredible records, and these guys were awesome at math. And they discovered this thing called the Saros cycle. And the Saros cycle is basically what causes total solar eclipses to occur. Now, this is without computers. But what they figured out was if they wanted to predict roughly when and where a total solar eclipse would happen, they needed to know three things. And again, it's the three things I talked about earlier. Where the Earth was relative to the moon, where they were relative to the sun, and where the orbit of the moon was on its tilting angle. So you had a month, a year, and this thing called the anomalistic month, or this tilt angle. When those three combine, they give rise to this crazy periodic variability, I guess is the right word, because it's not quite 18 months, and because these things aren't quite exact, the locations and times of the eclipses kind of vary very slightly. But typically, I shouldn't move, get in trouble. They typically follow the pattern. It's on the left-hand side of the slide here, this diagram illustrating the solar cycle of eclipses. 18 months. So typically on Earth, every 18 months, there's a total solar eclipse. They figured that out a long time ago. And in fact, the Greeks were so amazed and so wanting to one-up the Babylonians, because that's what they did. They built a computer. And in fact, the computer that they built was discovered in a shipwreck in 1901. It's called the Antikythera mechanism, and I don't know if anyone's seen the Nova Special, but that was pretty impressive. But since the Nova Special, they did some detailed X-ray studies of that box and identified that it actually had a plate at the back of it that could also predict eclipses. Didn't know that. So they're constantly finding the ingenuity of the Greeks. But that Antikythera thing is pretty cool. Now, as scientists, we also use eclipses for science. Right? We want to understand this mysterious cloud of stuff that appears, but we can't see it the rest of the time. Well, back in the day, they figured out that this mysterious cloud was about 1/1,000,000th the brightness of the disk of the sun. That makes it somewhat difficult to see in daylight. But back in 1868, during a total solar eclipse, these two non-friends, as all stands, Jules Janssen and Norman Lockyer, Sir Norman Lockyer, got to get that right, discovered helium by looking at the spectrum of the sun. So the light that came from the sun, they identified that there were certain key features in the electromagnetic spectrum of the sun that could only be there if there was an atom of a certain kind. And that atom they dubbed helium, the Greek for the sun. A few years later, Arthur Eddington decided to test this brand spanking new theory of general relativity. General relativity is all about space and time. In fact, general relativity is about the bending of light. And in fact, there's been a lot of fuss in the scientific community over the last few years because things called gravitational waves have been detected that are also related to this. But what Eddington decided to do almost 100 years ago, and what we hope to replicate next year, is what he tried to do was to look at a total solar eclipse and look at the positions of the stars that are very, very accurately known around the sun and see if the light that appeared at the eclipse was not quite at the predicted locations, i.e. the light had been bent by the gravitational pull of the sun. Lo and behold, 100 years ago, with no laptops, probably slide rules and gosh knows what, they demonstrated that Einstein's theory was correct and that the positions of these stars were not where they should have been. Now, just to whet the appetite a little bit, here's a total solar eclipse taken from Patagonia. And it's sped up 4.5 times. And so now you get to see the real kind of broad scope of what happens with the shadows and how things move, and whether you're in a partial eclipse or a total eclipse. And so you can see the sky extended out to either lobe of this, where they're not in total solar eclipse. That band of dark right about the sun is only about 70 miles across. But you see all 4 phases there as this thing goes through. I saw this movie and I couldn't help but include it. So, moon comes across the sun. There's the corona. Looks pretty cool. A minute and a half later, it's gone. Now, if you were having to rely on studying the corona through eclipses, that would be pretty rough. So, that big ball in the sky, the thing that goes to bed at night and wakes up in the morning without doing anything devastating to you all, luckily, is a complex object. It is a hydrogen nuclear furnace at its core. 2 hydrogen atoms live in a very dense, very hot environment, and they naturally fuse together to make helium. Now, I'll charge our younger guest here to figure out how many zeros are in that number. But the amount of energy that furnace produces is 386 billion watts of power. That's a fair bit. By mass, the sun is about 71% hydrogen, 28% helium, and a mix of other junk. Junk like iron, carbon, nitrogen, oxygen, it's a tiny amount. That accounts for about 99.8% of the mass of the entire solar system. It's all concentrated right down there at its core. 1.3 million of our little planets fit inside the sun. It has a density at its core of about 150 times that of water, so it's kind of mind-boggling place. And I will say, in case there's any astronomers in the room, that most astronomers consider our star to be a dull, middle-aged, boring thing. Just saying. I would tend to disagree. However, the part of the sun that you look at in the morning kind of looks like this. It's pretty vanilla. This is what we call the white light sun. This is basically the optical or the surface of the star. And it looks pretty boring, right? You can see maybe, if my pointer's working, a few sunspots, little tiny things here and here. But other than that, it's bland. That bland thing is at a temperature of about 6,000 Kelvin, 6,000 degrees. It's pretty hot still, but pretty dull. But that dull, boring thing turns away like a big pot of water. If we step up a little bit in the atmosphere and move to a layer, you can think of the sun a little bit like an onion. We start to see more structure. But there's this amazing thing that's starting to happen. That the outer atmosphere, the sun's away from the sun's surface, is actually starting to get hotter. Now, has anyone opened the door to their fridge and their kitchen got warmer? No, that doesn't make much sense, does it? You would think it would get colder. Well, the sun's atmosphere, as you get away from its surface, it actually starts to get warmer. Figure that one out. There's a Nobel Prize in that for someone. As we step up, again in the atmosphere, we start to see different features. And the fact that our boring vanilla star is kind of gone, and it's morphed. In this part of the sun, we need to get out of the Earth's atmosphere to see. This is in the ultraviolet. And you're starting to now see a thing called magnetic fields. We're starting to see the influence of magnetic fields on the outer atmosphere of our star. Like here, where the sunspots were, very strong concentrations of magnetic field, and you start to generate very, very hot gas or plasma. Pretty profound change now. So we now jumped up a few thousand kilometers, and we actually went over 1,000,000 degrees in temperature. So that corona that we saw in our eclipses was actually 1,000,000 degrees hot. Not cold, it's hot, very hot. I won't get into some of the conundrums about the corona. But that was one of the mysteries. How does, in fact, it's still one of the driving mysteries of our field, how does the outer atmosphere or corona of our star reach 1,000,000 degrees from an object that's only 6,000 degrees warm? Again, if anybody has the answer to that question, write it on a piece of paper for me and leave it here. Again, as we go to the even further out in the atmosphere, in the hotter part of a star, you start to see that these magnetic features take on a life of their own. In fact, this life of their own looks very much like a teddy bear. Can you see the mouth? Can you see the nose? Can you see the eyes? This is not Photoshop, people. That is basically what is happening is the magnetic field is starting to take over. So the sun has a very subtle balance between the magnetic field and the gas. And as the gas boils, it's like a pot of water. But if you put spaghetti in that pot of water and you get a good rolling boil, you see how the spaghetti just circles and circles and circles and tumbles. But it's just following what the water in the pot is telling it to do. Now the corona is the complete opposite. Could you imagine stalks of spaghetti now starting to stick out of the pot and water streaming out along them? Hold on. But that's what's happening here. And as you go out even further, now this is a set of images that go out to 40 solar radii. And you're starting to see how well-defined and how beautiful and extended that corona is. And in this movie, in the top right-hand side here, you actually start to see how violent that place also is. And because we look at it in Eclipse, and we only see it for 2 minutes at a time, you don't really get a sense of just how violent and nasty that place is. And it's violent and nasty because the magnetic field at the very bottom of the object changes all the time. So with a very special piece of hardware called a magnetograph, we can actually look at the magnetic field, the little magnets on the sun. And this is just an image of the magnetic field. The white patches are positive polarity, or north poles, and the black patches are negative polarity, or south poles. And on the image on the right, you can see how these things rotate and change over the course of a month. But that magnetic field is just constantly being driven around and changing. Now, it's just like any other thing that you want to twist around. You can think of a slinky. You take a slinky and twist it, eventually it goes boop. The sun's magnetic field does that too, with often dramatic effects. Now, I should tell you, if you don't think this is really important, that magnetic field and the gas and the light and the energy that follow that magnetic field out from our star actually inflate the solar system all the way out past Pluto. So you can think of it as pulses of magnetic field come, the energy that flows from the star changes, and it causes our solar system to inflate and contract, just like a big jellyfish. And we're only just starting to understand this. Now, the corona, it's pretty violent. Our little planet lives in that space. Now I show you a beautiful illustration of our place in the solar atmosphere a little bit ago. But does that look like a place you want to live? Now again, there's 40 solar radii. You can see comets whizzing through here. There's actually Saturn's over here. It's just a blip. But these things are streaming through our interplanetary space at thousands of kilometers a second. These are all charged particles. This is not good stuff, especially not if you live on the space station or somewhere else. Like I said, these things, these objects that you saw in that last movie are called coronal mass ejections. And they pose a significant threat to Earth. In fact, they pose a significant threat to most of the planets. But since we're here, it actually makes it quite important. As these guys whip around the backside of the Earth's magnetic field, they drive energy back down into the system and produce something quite beautiful. You know what the beautiful thing is? But just remember, the next time you see the northern lights or the southern lights, it's a signature of something kind of nasty taking place. Okay? Again, from space, looking down from the ISS, from the International Space Station, the aurorae are truly spectacular. Looking from the side of a loch, they're also pretty spectacular. See them dancing, and that dancing is because of the energy that's been deposited in the Earth's magnetic field way out on the back end, on the what we call the night side of the Earth, that streams back in and dumps energetic particles into the Earth's atmosphere. This is bad news if you have power grids. Bad news if you have telecommunications satellites. Bad news if you have GPS navigation system and you really need to be at your appointment at this time. No, I'm kidding. It's bad news if you're making large visa transactions. You know, anything actually that is time tagged is vulnerable to coronal mass ejections from the sun. And in fact, you know, by military aircraft and astronauts in space, it's been projected that it costs the government and industry about $10 billion a year of slop. $10 billion a year of something you've got almost absolutely no control over. But we can predict it, maybe. Now, 75 years ago, our lab here at NCAR, the High Altitude Observatory, was put together to help understand the disturbances that came from the sun. This is a beautiful example, which is over a solar diameter across in 1945, and how they disturbed the Earth's atmosphere like the aurorae, and what knock-on effects they had for telecommunications. Why in the 1940s was that important? Well, because they'd already started to figure out that the guys in the battlefield were having problems with their communications. And those problems with their communications were all to do with solar activity. And so they sent a young postdoc out to the pristine Colorado mountains to observe the sun and telegraph back to Washington what was going on. And that became the start of the High Altitude Observatory. Out in the foyer there, you'll see this object, the Eclipse chronograph, on, I believe this is in the Sudan, in the mid-60s, and it has more miles than I care to mention. But that is truly a piece of, a museum-level piece of kit out there. Now, the HAO of the modern times both observes the sun and models the sun. But beyond that, we model and observe the interaction of our planet with the sun. We try to understand how the energy and mass that come from CMEs interacts with our upper planetary atmosphere and cascades down to the point where it can impact communications, GPS, etc., etc. And of course, next year, we hope to be flying on an experiment on the NCAR NSF G5 aircraft, which is stationed, some of you might have seen it flying around Broomfield from time to time when it's home, to try and chase the eclipse next year. Now, as we get on to the eclipse of 2017, we get a quick look at all the total solar eclipses that have taken place in the 21st century, of which there are many that have crossed the continental US. And in fact, if you look very carefully, right up the middle, this once-in-a-lifetime event isn't really, because it's a twice-in-a-lifetime event. All right, so let's see if I can get my mouse to work. It's not working. Works on some slides, promise. But the August next year's eclipse, you can see going right across all the way from Oregon to South Carolina. But the 2024 eclipse will go up from Mexico City over towards New York State. And so both are going to be pretty spectacular opportunities to study the corona, but also for us to explain to the general public what we do and why we do it. Now, if you want to get out to the West Coast for 10:16 Pacific Daylight Time on August 21st, 2017, I recommend you do it. Or if you want to scoot across the country in 91 minutes, you can do that too. Yes, the eclipse will take 91 minutes to cross the entire country. The sky will be dark on that path of totality for approximately 2.5 minutes on average. The path of totality is only 65 miles wide. If you're out with the path of totality, remember it's not total. You'll just be in partial daylight. You'll be in like twilight for a little bit longer. The grand eclipse, or the position of where the eclipse will be longest, is in Lexington, Kentucky, and I believe that's where our aircraft project will be located. Their totality will be 5 minutes because they can't quite keep up with the sun, or the moon shadow, but they're going to try. It'll be 5. So all of the lower 48 will be in shadow. Eclipse path crosses 12 states. So you will get to see the corona without millions of dollars worth of fancy equipment. Thank you, it's my pleasure. Now, if you can watch this thing scooting by, this is a pretty awesome movie that one of my friends put together that hopefully will play. Yeah, it's playing now. And so what this is a Google map. And on that Google map is superposed the shadow of the sun. You can see the time changing. And so you can go on to this incredible website, greatamericaneclipse.com, and look and try to identify your hometown, where you want to be on the eclipse path as it crosses from Oregon into Idaho, into Wyoming. Yeah, Casper, I heard that. Into Nebraska. There'll be 5 people in Nebraska at that time. Across Nebraska, necking into Kansas, across into Missouri, crossing, just passing Kansas City, just skirting underneath St. Louis. It's going to be cool. Now, do you think that the 100 million plus people that go to this line of totality to see the eclipse are going to make our country crease in half? Now, word of advice. Here's the warning. No, I'm kidding. The warning comes next. if you're going to do this, there's this thing called weather, and there's these objects called clouds. And as a Scotsman, you don't want to be a theoretical solar physicist, because in Scotland, that's all they have. Because we never see the sun. Which is why I moved to sunny Colorado. But anyway, other than that, they've taken 22 years worth of meteorology data from space and compared the cloud cover. And they've looked at both the AM and the PM. And in these graphs, blue is good, red is bad. And so typically, us being in the West are in great shape. In the mornings, before noon, we've got chances of very clear skies that day. If you're out in the East Coast, because the convections have a chance to kick up in the heat and humidity, it may not be great out in the east. So what they're projecting is the best places to look are Northern Oregon, Idaho, Central Wyoming, and Western Nebraska. So there may actually be more than 5 people in Nebraska. And so I took a little bit of a snapshot out of this. And it's all relative to Boulder. So if you want to drive to Madras, Oregon, it's 1,100 miles and a 17-hour drive. Giddy up. But Casper, Wyoming is 278 miles from here and will be a perfect site. Don't quote me on that. Equivalent to that will be Gandy, Nebraska, out in the southwestern foothills, and that'll be good. I believe there's a massive, massive event planned in St. Joseph, Missouri, right on the border of Kansas and Missouri. And pretty much after it gets across that point, you're going to have to be in a plane. I don't know. I'm being skeptical, but it may be difficult after you get to that point because it's now getting much later in the day. But my fingers will be crossed. Now, how do you want to view this thing, even when you're out there? Of course, during totality, I will tell you, having seen one, you don't want to be looking through any of these objects when the eclipse is total. Take everything off. Look at it with your naked eye because the cameras do not do it justice. If you've got a tripod, an automatic gizmo, remote control, let that do the work. You can buy binoculars, both regular binoculars and special sun-filtered binoculars to see the eclipse, to see the path. If you buy binoculars, we should also buy some of this stuff. Number 14 welder's glass. You can get it for a few bucks at McGuckin's. And all you do is just pick it up, look through it. It blocks out all the harmful rays for the sun. When the Pac-Man has stopped, when it stopped taking bites out and we get to totality, you just put it down. Watch the majesty and remember third and fourth contact? That's when everybody just starts yakking. Wasn't that amazing? Oh yeah, that was cool. So there's also this thing called a pinhole camera. Has anybody ever built a pinhole camera? All right, you can build pinhole cameras. You can even put holes in pieces of cardboard and project it down onto the sidewalk. There's so many ways you can do this and so many things you can do. But the general rule of thumb is do not ever look at the partially eclipsed sun with the naked eye. By all means, though, look at the eclipsed sun with it. Now, we run this little project that actually kicked off in 2012 called the Eclipse Mega Movie Project. We won't go with its acronym of EMP because it seems to scare some people. It's a joint project between the University of California, Berkeley, NCAR, the NSF, and this company with a G for a logo. Now, there are many excellent projects out there, and my friend David Elmore is going to take part in another similar project that's out there. And the idea is to both engage and train, educate the general public about the sun, its connection to the earth, why we study it, but also to think about the images that they're capturing. We want to get professional and citizen observers out there. We want to take 1 million frames of the sun as its 91 minutes transit across the earth. Not a lot, actually. But if you play back that movie in a regular theater, you could be watching for hours and hours and hours. That'd be awesome. Now, I'll show you some of the images, some of the several thousand images we got in Australia. Unfortunately, the bandwidth in Queensland wasn't fantastic. And so we only got a few thousand. So we got our kilo movie, not our mega movie. But what we hope is that the professional astronomers or the amateur astronomy groups will have pretty good gear out there. And so we're going to actually have 3 types of movie for the Eclipse itself. We'll have the Terra movie, which is everybody and their cell phones. We'll have the Mega movie, which will be probably people with DSLRs and slightly higher end equipment. And then we'll have another Kilo movie. But that Kilo movie will be taken with things like IMAX cameras. That'll be pretty cool. Now, and I forgot to do this. Does everybody have a pair of these? You know what they are? They're Eclipse glasses, right? And so like a fake version of welder's glass. Much cheaper, much lighter. I dare everyone to put them on. You won't see much, but I do get to take a picture of all the nerds in the room. Thank you. Please take them home with our compliments and try and keep them for next year. I do believe that wherever you go to see that eclipse, there'll be some of those handy. Because every company in the world that makes them is spinning up rather rapidly. Now, for young and old, a chance to win a t-shirt like mine. Now, you'll see outside, there's a sheet of paper with an Eclipse disc on it. Grab a crayon, grab a pencil, and try and sketch for us what the total solar eclipse next year might look like. We're not giving special awards for predictive capability, although I may be contacting you for a job. But we will be looking at originality and imagination, and so I would encourage you all, if you want, to take part and submit one in the box. I want to finish with a brief dedication to a dear friend who passed away last week. After 40 plus years of service at NCAR and the High Altitude Observatory, we lost a dear colleague from a very aggressive, rapidly onsetting pancreatic cancer. And he will be truly missed, and I look forward to Wednesday afternoon when we can have a memorial service out on the Tree Plaza for Vic. And with that, I'm going to leave you with one more piece of eye candy, taken from an airplane in March of this year, out over the Pacific. And I would like to thank Yaga Richter for herding me, Paul for herding us, my administrative assistant, Cheryl Shapiro, for herding everybody, Larissa here for signing so beautifully in Scottish, the NCAR education staff and Tim for giving amazing tours of this wonderful facility, and to all our student volunteers for helping check you in and seeing you safely through our building. And thanks very much.